questions 21 through 25 on the 2015 grade 11 Fermat math contest. Amina and Bert alternate turns tossing a fair coin. Amina goes first and each player takes 3 turns. The first player to toss a tail wins. If neither Amina nor Bert tosses a tail, then neither wins. What is the probability that Amina wins? So we have Amina and Bert, turn 1, turn 2, and turn 3. So Amina will win if she gets a tail. So let's say she gets a tail on the very first try. Well, what's the probability of that? Well, when she flips a coin, it's half that she gets a tail. Okay, that's one way of winning. Let's say she doesn't get a tail, she actually gets heads. Well, then we now go to Bert. Bert has to lose because we want Amina to win. So Bert loses if he gets heads. And then we go back to Amina for her turn, which is turn 2. And at this time, she gets a tails. Okay, so now we have to calculate this probability. So it was the scenario where she got heads. So there's half probability of that. Then Bert got heads. So multiply by a half. And then when we went back to her, she gets tails. So half probability of getting tails. So that's that scenario. Now we have the third and final scenario where she got heads, then Bert got heads. Then on her turn 2, she got heads again. Bert got heads again. And then finally on turn 3, she wins by getting tails. So we have to figure out the probability of this scenario. So it was heads first, so 1/2. Then heads for Bert, 1/2. Then heads again for Amina, half probability. Heads again for Bert, half probability. And then finally tails for Amina, half probability. And then now we have to add all these guys up. So it's a half, and then this is 1/8. And this whole thing is 1/32. So we'll get a common denominator, which would be 32, and the numerators would be 16, 4, and 1, and that's 21/32. 21/32 is choice A for number 21. 3 distinct integers, a, b, and c, satisfy the following 3 conditions. A, b, c, a times b times c, that is 17955. A, b, and c form an arithmetic sequence in that order, and 3a plus b, 3b plus c, and 3c plus a form a geometric sequence in that order. What is the value of a plus b plus c? Well, on the side here, let's just figure out what they are referring to. A, b, and c form an arithmetic sequence, so that means they are of the form a plus d, a plus 2d, right? That's what it means to be an arithmetic sequence. And then these 3, which are 3a plus b, 3b plus c, and 3c plus a, form a geometric sequence. So that means they're of the form a times r squared, because that's what it means to be a geometric sequence. Okay, so let's now work with this, with our goal eventually finding a plus b plus c. Well, in a geometric sequence, which is what these guys are, if you take the second one and divide by the first one, it will give you r, right? Because the a's cancel. But the same thing happens if you take the third one and divide by the second one. Again, you'll get r, because ar cancels on top and bottom. So that's what we're going to do, but with these guys. So take the second one, which is 3b plus c, and divide by the first one, which is 3a plus b, and that's going to be the same as the third one, which is 3c plus a, divided by the second one, 3b plus c. Okay, now let's cross multiply. So we have 3b plus c times 3b plus c And then on this side, it's 3c plus a times 3a plus b. Okay, but before I cross multiply, I want to substitute what is a, b, and c in terms of my arithmetic sequence. Because right now there's 3 variables, and it would be nice if I can get it down to just 2 variables. The less number of variables, always the better. Okay, so in a very careful way, let's substitute what is a, b, and c. b is a plus d, right? I'm looking at these guys right here. What is a, b, and c? C is a plus 2d. And very similarly, the next one is also exactly the same. It's 3b plus c, so it's 3a plus d plus a plus 2d. That takes care of the left side. The right side is going to be 3 times c, which is a plus 2d plus a, and a is just a. And then 3a plus b, which is a plus d. Okay, so we've got it all substituted. Now let's simplify. So this is going to be 3a plus 3d plus a plus d, 2d. And this is pretty much the same thing. 3a plus 3d plus a plus 2d. This on this side is 3a plus 6d plus a, and this is just 4a plus d. All right. Let's simplify this. So we've got here 4a plus 5d, 4a plus 5d. On this side we have 4a plus 6d, and this is 4a plus d. Okay, now finally we can expand. So expanding, we get 16a squared plus 40ad plus 25d squared. On this side, we get 16a squared plus 4ad plus 24ad plus 6d squared. All right, let's simplify everything, put it all on one side. And when I do, I get 19d squared plus 12ad is equal to 0. Okay, I can divide through by d, and that will just leave me with d 19d plus 12a. And therefore, if this is 0, d is not 0, because if d was 0, it wouldn't be a arithmetic sequence, really, because there's got to be some sort of difference. So this is 0. So that means 19d plus 12a is 0. And then let's isolate for one variable. So minus 12 over a over 19 is d. Okay, so this is a very important finding. Okay, pretty good progress there. Now let's use the fact that a times b times c is 17955. That's given in the question. And as we had written, since a, b, and c are an arithmetic sequence, a is a, b is a plus d, and c was a plus 2d. And this is really the last step of a relatively late stage question. So it's pretty good that we were able to do this so well, so quickly. So we'll substitute for d, and we'll have just one variable. So minus 12a over 19. And on this side, we've got a plus 2d, so that's going to be minus 24a over 19. And that's 17955. All right, so let's do this math here. We got a. This will be, if I get a common denominator, 19 and 19, top and bottom, that's going to be 7a over 19. And this one, same thing. If I get a common denominator, top and bottom, that's going to be minus 5a over 19. 17955. Okay. Do this math. You got minus 35a to the power of 3, and then 17955 times 19 squared. Okay, so pretty big numbers here. And if you multiply this all out, you get minus or rather plus 6, 4, 8, 1, 7, 5, 5, minus 35, a to the power of 3. Dividing through by negative 35, and you will get minus 185. 193 is a to the power of 3. And you take the cube root of this, and when you do, out pops a perfect integer, namely negative 57. All right, great, wonderful. We are pretty much in the final stage now. A is this. We can easily plug that into here to get D. D will be minus 12 times negative 57 over 19. And when you do that math, you get D is equal to 36. All right, well, B was A plus D. So B is going to be minus 57 plus 36. And that means B is equal to minus 21. And C was A plus 2D. So that's going to be minus 57 plus 2 times D, so 72. So that means C is 15. So there's A, there's B, there's C, and our final step is calculating A plus B plus C. So that's minus 57 minus 21 plus 15, and that is minus 63. So the answer to this cool question, number 22, is A. How many pairs xy of non-negative integers with 0 less than or equal to x less than or equal to y satisfy the equation 5x squared minus 4xy plus 2x plus y squared is equal to 624? So this is a question that involves algebraic manipulation, and all it really takes is some practice and some confidence. So we have to get this equation in some sort of a form that will help us, and right now it's not really in any such form. So we have to manipulate it. Now at first, of course, I don't know how to do it. So what I'm going to do is just look at these terms here. Well, I've got a 5x squared. Okay, I'll put the 2x there. And then I've got a y squared. Put the minus 4x. Just trying to group things to see if anything comes to mind, because I want to talk you through it. I don't want to just give it to you the solution, because otherwise you'll think, well, where did that come from? How would I know how to do that? So far I just rearranged it a little bit. No big deal, right? But then you think, okay, well, these are squares here, right? So perhaps it was some sort of a square, something plus something squared or something minus something squared. Okay, so let me concentrate on this guy. There's an xy here. It's a little bit complicated. So maybe it was something like y and x squared. Well, if you square that, it becomes 2xy plus x squared, like that. Okay, well, that's not exactly this, but it's, okay, we're getting somewhere. This is a 2, this is a 4. So instead of y plus x, how about I put plus 2x? But I don't want to put plus 2x, I'll put minus 2x. I think that's the only way I'll be able to get a minus. If I do this, let's see what we get. Y squared minus 4xy plus 4x squared. Okay, that matches at least those two terms. Well, this is a problem, but it's actually not, because I've got 4x squared there, at least if I break it up. So let's do that. And let's break up that 5x squared into an x squared and a 4x squared. And then let's keep that 2x. And then we keep this y squared minus 4xy. And when I do that, you will see that this is exactly like that. So as you can see, it takes a little bit of practice, but if you can do quite a few of these, you'll get a very good hang of it. So this now beautifully factors into y minus 2x squared. Okay, but we still got these ones. X squared plus 2x. And then we've got this 624 over here. Okay, so what do I do with that? Okay, so I'm purposely doing this step by step to ensure that you understand. Again, I would like to have this sort of in this form. Well, that can be done in a more easier way by completing the square. And you guys definitely know how to complete the square. Well, just in case you forgot, you take half of this and square it. So x squared plus 2x, but then you take half of this coefficient and square it. So half of 2 is 1. The square of 1 is 1. But then you have to immediately subtract it as well. And then the rest can stay the same. And what that does is allows you to beautifully factor this. It becomes x plus 1 squared. Great. And then this is y minus 2x squared. But then don't forget, you got this lone negative 1, so let's just throw it onto the other side, making that 625. So now I've got something that I can work with. So in a very, I think, reasonable way, without too much complicated algebra, we were able to create this form. And this is the form that is going to help us solve the question. So how is this going to help us solve the question? Well, let's talk about this. We've got two perfect squares, right? This is something squared and this is something squared. And when you add them, it's got to equal 625, which itself is a perfect square, by the way, as I'm sure you know. So what we do is we'll make a table and look at the different scenarios and take it one step at a time. So here we go. So in this table, this will be x plus 1 squared. This will be y minus 2x squared. This will be x and this will be y. So we have to get positive integer pairs. So here we go. Well, the first one is the most obvious one. I think that is 0 and this is 625. And then you're allowed to use a calculator so you can fiddle around. What perfect square can I put in this column? And what perfect square can I put in this column to make it add up to 625? And a little bit of fiddling around, you get the following. 49 with 576, that'll work. Those are both perfect squares. Then you keep going up the list and you'll find the next one is this one. 225 and 400. And then 400 and 225. Then they just reverse. 576 and 49. And then finally 625 and 0. It's actually not as time consuming as you think, because each of these are really just like this, for example, was 7 squared. So you really only have to go through 25, because 625 is 25 squared. So don't think that I had to go through 1 and 2 and 3 and 4 and all the way up to 625. No, I just had to treat this guy as either 0 or 1 or 2 all the way up until 25. And when I did, when you square it, it became these large numbers. So going from 0 to 25 isn't that time consuming. You can do it pretty quickly on a calculator. Okay, now what we have to do is we have to figure out x and y for each of these. So how many do we have? 1, 2, 3, 4, 5, 6 different scenarios. So here we go. So let's start one at a time. The first one right there. X plus 1 squared is 0. So that means x plus 1 is 0. That means x is negative 1. Well, right off the bat, this one is no good, because x and y both have to be positive according to the question. Okay, no problem. We just eliminate that one. Just put a big X there. Let's try the next one, which is this one. So x plus 1 is equal to 49. X plus 1 squared, that is. So x plus 1 will be plus or minus 7. And x, therefore, will be 6 or negative 8. We only have to worry about the positive, so let's just look at 6. And then now we look at this one, which is y minus 2x squared is equal to 576. We are using, again, square roots, so we have to take the plus and minus. Don't forget that, and I think that's a part of the question that people will miss and end up getting the question wrong, that they forget to do plus or minus. So when you take the square root of 576, it's 224. We have chosen x to be 6 since it has to be positive, so that means y minus 12 is plus or minus 24, and therefore y, when you do the math, is going to be either 36 or minus 12. Well, y has to be positive, so use the 36. So there we go. We got one pair. Okay, so let's go with the next one, 225. X plus 1 squared is 225. So take the square root, x plus 1, therefore is plus or minus 15. X is therefore equal to either 14 or negative 16. We use the positive value. Then this equals that. So y minus 2x squared is equal to 400. So y minus 2x is equal to plus or minus 20. We have set x equal to 14, so that's going to be y minus 28 is equal to plus or minus 20. So y is going to be equal to either 48 or 8. All right. That means we got 2. But be careful. This question is a little tricky, not extremely tricky. Because you think, okay, great. I got 8 and 48, so I got 2. But if you remember, the question says that x has to be less than y. And that's something that you may have forgotten. It has to be less than or equal to y. So, based on that fact, we can't use the 8 because 14 is certainly not less than or equal to 8. So the 8 cannot be used. The only one we can use is the 48. All right? Okay. So same thing. By now you're an expert, so I don't have to talk you through it. I'll just do the algebra. X squared is 400. Take the square root. X plus 1 is therefore equal to 20. X plus or minus 20, that is. And therefore x is equal to 19 or negative 21. And of course we just want to use the positive one. And then this is going to be equal to 225, so do that. Y minus 2x squared is equal to 225. Y minus 2x is equal to plus or minus 15. X is equal to 19, so this becomes y minus 38 is equal to plus or minus 15. And solving, we get y is equal to either 53 or 23. And both of those are greater than 19, so those are both admissible. So we'll put 23 and 53. So both of those are for 19. So I'll just write 19 twice just to indicate that there's 2 of those. All right, so I hope you're getting the hang of this. Same thing. We got to do a little bit more algebra here. For the next one, it's going to be 576. X plus 1, therefore, is 24. Plus or minus, that is. Just like to be thorough here. And therefore, x is going to be equal to 23 or minus 25. And of course, you're going to use the positive value. So 23. And then y minus 2x all squared is equal to 49. That means y minus 2x is equal to plus or minus 7. X is equal to 23, so y minus 46 is equal to plus or minus 7. Correct? So that means y is equal to 53 or 39. And both of those are admissible since both of those are bigger than 23. So there we go. And we are almost done. We've got one last one. X plus 1 squared is 625. That means x plus 1 is equal to plus or minus 25. X is therefore equal to 24 or negative 26. We use the 24 since it's positive. And then finally, y minus 2x squared is equal to 0. Y minus 2x therefore equals 0. Y is equal to 2x. Therefore, y is equal to 48. And there we go. We're done. So pretty good, right? How many did we get? 1, 2, 3, 4, 5, 6, 7. We got 7 ordered pairs. And therefore, number 23, the answer is E. In the diagram, two circles and a square lie between a pair of parallel lines that are a distance of 400 apart. The square has a side length of 279, and one of its sides lies along the lower line. The circles are tangent to each other, and each circle is tangent to one of the lines. Each circle also touches the square at only one point. The lower circle touches a side of the square, and the upper circle touches a vertex of the square. If the upper circle has a radius of 65, then the radius of the lower circle is closest to. Let's draw some lines and then let's talk about this question. So the first thing is the centers have to meet of those two circles since they're tangent. And then I will draw a line from the center to where it touches that bottom line. Then from the center to where it touches the square. From the center of the small circle to the vertex where it touches. And anything else that we need, well, I can continue to draw a line from the center of the small circle to the top right there. One line from top to bottom, just to illustrate the fact that that's going to be 400. And then two triangles, one that goes directly down from here to the bottom like that, so that's a right angle. And then finally one that goes from the vertex across like this. So that is a right angle. And that should be it. Okay, now let's start labeling. The question tells me that the distance from the top to bottom is 400. So this is 400 right here, that top to bottom distance. The square has side length 279. So all of these guys are 279. 279, 279, and so on. Okay. And then let's start labeling the radii. Well, this is 65. That's actually given as a number. So that's 65, that's 65, that's 65. And then the radius of the big circle, we don't know. That's actually what we're trying to figure out. So I'll just call it R. So R, R, and R right there. And then that is pretty much all from the question. Now, I introduced two little triangles, right, that are sort of written in orange. So I've got to introduce one more variable. That's the good news, that there's really only one more variable, and then I'll call it x. And that x is the distance from here to here. So there we go, that's x. And it's the same up there, so that's also x. Okay, so that means the distance from here to here is r minus x, right? And finally, this distance top to bottom, I will call h for height. And that should be it. So let's begin. Now what I'm going to do is, in order to avoid making the diagram messy, those two triangles, I'm going to draw them below. So the first triangle, the one with the h, I'll just draw it right here. And the small triangle, the one with the x as the base, I'll draw here. And then we can work with them. So let's label those. 65, x, this was r minus x, and this was h, and this is r plus 65, directly based on what information we had above. Okay, but I don't have this distance here, but that distance I think I can figure out. The distance from here to here is 279, and the distance from top to bottom is 400. So that means the distance from there to there has got to be 400 minus 279, correct? 400 minus 279. And that, of course, is 121. So if the distance is 121 from there to there, that means this is 121. So that means this is 121 minus that 65, correct? So 121 minus that 65, and that is 56. So very quickly I can get a Pythagorean relationship. 56 squared plus x squared is 65 squared. Correct? And when you solve for this, you get x is equal to 33. So no problem. Okay, now let's turn our attention to this guy. This is going to be obviously a little bit more complicated, but the basics is the same, that it's Pythagoras. So I've got r minus x squared plus h squared is r plus 65 squared. So let's expand this, and we got r, but x is 33, so I can just put 33 in there like this. Expanding, we get r squared minus 66r plus 33 squared plus h squared equals r squared plus 130r plus 65 squared. Okay. H squared plus 196r, and then 65 squared minus 33 squared will give me 3136. Okay. And therefore, h is going to be the square root of that, obviously, 196r plus 3136. All right. So you might say, okay, I've got h in terms of r in terms of h. Where do I go from here? Well, the good news is we can use this 400. Every piece of information they gave us in the question was given for a reason. And what that relationship gives us is that if you look at the top to bottom height, right, it's 400. Now let's look at it from our diagram. It would be 65 plus that h plus the distance from there to there, which is just r. So that gives us another equation, 65 plus h plus r. And that equation is what we will substitute this finding into. 3136, that is. All right, so that's what we have boiled down the question to. So let's work with that. So we've got 400 plus 65, or minus 65, that is equal to h plus r, but h is this big long radical plus 3136 plus r, like that. Okay, I'd like to get rid of that radical, so this is going to be 335, bring the r over, and then what I can do at this point, since the radical is all by itself, I can square both sides. If I square both sides, this becomes 335 minus r all squared, and on this side, the radical will disappear. And that's great. Now we can work with just basics, algebra. Okay, now we have to expand this, so some big numbers will appear, so just don't make any algebraic mistakes. So this will be what, 670 r plus r squared, and this side doesn't change, so at this point. Okay, now let's put everything on one side. I think I can do that. R squared minus 866r, and then 335 squared minus 3136. So that's going to be what? 112,225 minus 3136, and that all equals 0. Okay, so I'm almost at a point of a quadratic, and I just have to make that 109,089. There we go. Okay, so now it's just a quadratic. So here we go, quadratic formula. Minus b, so 866 plus or minus the square root of b squared. 866 negative squared minus 4ac, 109,089, all over 2a. Okay, so this is 866 plus or minus, let's see here, 749,956 minus 4 times that, 109,089. That's going to be 436,356 all over 2. Okay. And let's see here, 866 plus or minus. So that's going to be 313,600. And then finally, at this point, you take the square root, and we get approximately, or exactly, 560. Great. And we're going to get 2, but the answer choices were all around 150, if I recall. So I'm going to take the negative root. So 866 minus 560 divided by 2, and when I do that, I will get the following, and I get r equal to 153 exactly. Perfect. Go back to the answer choices, and you will see that number 24, 153, is choice C for this excellent question. There are f fractions m over n with the properties m and n are positive integers with m less than m. M and n over n is in lowest terms. N is not divisible by the square of any integer larger than 1, and the shortest sequence of consecutive digits that repeats consecutively and indefinitely is in the decimal equivalent of m over n has length 6. We define g is equal to f plus p, where the integer f has p digits. What is the sum of the squares of the digits of g? Well, we start with a simple example to illustrate what we need to do. So let's say I have some number. I'll just make up a number. 0.58, 123, 123, 123, and so on, where the 123 is obviously repeating. Now I want to create a sort of a fractional form of this. So what I'm going to do is show you how to do that. And then we can extrapolate to other similar sort of numbers. First thing is multiply both sides to get this part into an integer. Well, in this case, I would have to multiply by 100 to bring it over 2 decimal points. So it would be 58.123 repeat. All right? And then what I can do is bring over just the integer part and then leave the decimal part on the other side. 123 repeat. Now I want to do this again, but I'd like to do it in a way so that I bring at least one repeat to the other side of the decimal. Well, in this case, it's only 3 digits that repeat, so I have to multiply by 1,000 in order to do that. So I've got to multiply by 1,000 on both sides to get part of it over to the other side of the decimal. So 123 times 123 repeat. Okay, so again, bring the decimal part separate from the integer part. So I do that by bringing over the 123 to the other side, and then on this side just leave that 0.123 like that. Okay, well, this 0.123 we already have in terms of n, so substitute it in. 100 n minus 58. So as you can see, I got rid of all the decimals, and I can write a nice formula without decimals to represent this big long decimal, which is n. Okay, so far this is how far we've gotten. And then now let's put the 123 on the other side and put this on that side. So 1,000 times 100 n minus 58 and minus 100 n minus 58. Okay, let's factor out that 100 n minus 58 since it appears twice. And when you do, you get 1,000 minus 1. Okay, we are almost ready to isolate for n. And it looks like 123 over 999, correct? And then that's going to be 100n minus 58. And then 123 over 999 plus 58 will be 100n. And then finally we'd have to divide through by 100. But before I do, let me just multiply top and bottom here by 999 to make sure we get the same denominator. And then now I can divide through by 1 over 100. 123 plus 58 times 999 over 999. Okay, so that big long process was to show that any such decimal with repeating digits can be converted into a fraction in a very similar way. So you can sort of do the same kind of story with any such decimal expression. But we have to get sort of a general term. This isn't great. This was only for this specific. It's meaningless, really. But it gives you a little bit of a pattern, and that's what we are looking for. So let's talk about it. We have n. We've got this thing, which don't really need to concentrate on too much, so I'll just call it k. But what's on the bottom is important. It's 100, which I'm going to write as 10 to the power of 2. And we've got 999. Okay, so this is where we have to recognize what is happening. The 2 right here comes from the fact that there was 2 digits there. Okay, correct? 5, 8, 2 digits, that's why there's a 2 there. Because remember, initially I had to multiply by 10 to the power of 2 in order to get that 5, 8 to go on the other side of the decimal. The 9s correspond to the fact that there's 3 of those digits that repeat. The digits that repeat were 1, 2, 3, right? 1, 2, 3 repeats itself. And there's 3 of those digits, that's why there's 3 9s. So, what I can do is I can sort of make a little bit of a general formula as follows. N is going to equal some integer. The numerator actually is not really that important. But what is important is 10 to the power of p times 9 dot 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 9, where the number of 9s is q. And the p represents how many digits I have here, and the q represents how many digits I have there. Okay, so I hope that makes sense. I know it's a little difficult, but so far, hopefully it's not too bad. Okay, so we are not interested in this specifically. That was just an example. We are interested in m over n. And m over n is going to be of some form. We have no idea, but it's some form, like we're going to have, obviously, a 0 followed by some whole bunch of A1, A2, some digits all the way up until, say, AP. And then what's going to happen is we are going to have 6 repeating digits. B1, B2, B3, B4, B5, B6. Remember, it's got to be at least 6, so I'm going to start with 6. Now let's look at what that formula will look like. Well, the k, remember, the numerator is not that important, but the 10 to the power of p, because there's p of them. Remember, there's p digits there, so that's going to be 10 to the power of p. And then this part, you put 9s, but how many 9s? Q 9s, and in this case, my q is 6. So it's going to be 999, 999. Okay? So that is the first step of the question. Now let's cross multiply, and when we do, we get nk is equal to m times 10 to the power of p times 999, 999. Now, since m over n was in lowest terms, that means n must be a divisor of this. So let's first list what are the prime factors of that big long number. Well, first we'll break it up into 2 to the power of p times 5 to the power of p, and then the 999, 999, that is 3 to the power of 3 times 7 times 11 times 13 times 37. So that means n contains those prime factors. And therefore, we can conclude that n must be a divisor of those prime factors multiplied together. And when you do multiply them all together, you get 1, 1, 1, 1, 1, 1, 0. So this is a very important number. All right. So that means m over n is of the form some numerator we'll call it S, over that very important number. And now let's revisit our criteria. The first criteria is that m has to be less than n. Okay, so that means S has to be less than or equal to 1,111,109. It's got to be less than n. And it's got to be positive, so obviously greater than or equal to 1. The next criteria is that m over n has to be in lowest terms. Okay, I think we can do that for any such m over n. We can always lower it, so can be done, whatever it is. The next criteria is that n is not divisible by any square. And that is true because we don't have any perfect square in the prime factors. We have individual prime factors. So if you look at the prime factors, you will see that that's not going to be an issue. Because if we had, like, for example, something like 7 squared, then yeah, but we have just individual prime factors that make up this number. And then now we have to look at the fourth criteria, which is the toughest one, which is that m over n is of the form that it repeats, and it repeats 6 times, at least 6 times. So it's basically of the form 0 and then a whole bunch of a's, ... until some AP. These are not repeating, but then we've got at least B1, B2, B3, B4, B5, and B6 that repeat. So now we have to concentrate on this guy right here, this one. So we have to get this S over 1,111,110 into some form that shows that it will look like this. Okay, well, this is where some fancy algebra comes in. We can factor out a 1 over 10 and put a 9 up there, and then here we'll get 999,999. I just manipulated this number a little bit. Nothing has changed. Now this can be written, we can factor out the 1 over 10, and we can break it up into an integer and a fraction. So if this is divided by this, there would be some integer and then a fraction that's left over. So I'll let y represent the integer, and the fraction I'll represent as some numerator over 999,999. And then again, the integer we're not so worried about, but the numerator, which I denoted as z, that one is obviously going to be something less than this 6-digit number. Now it could be less than 6 digits, but it has to be at most 6 digits, so I'll call it a 6-digit number, R1, R2, R3, R4, R5, R6, like that. And the denominator is that 999,999. Well, when you multiply through after you adding it, it will look as follows. First, when you add this, it becomes y dot R1, R2, R3, R4, R5, R6 all repeat, because that's what happens when you divide by that number. And then finally, when you divide through by 10, it will bring the y over one space to the other side. And then we have R1, R2, R3, R4, R5, R6 all repeating. So I showed how this can indeed look like that format. So far so good. So now we have to figure out how many of these fractions can we make. Well, we noticed that the numerator can be anywhere from 1 to 1,111,109, and every one of those numerators will create one separate fraction. So that's how many we will get. But here's the thing. We will also sometimes get shorter sequences because we have to have sequences that are at least 6 in terms of the repeating part of it. So we have to look at how many shorter sequences we have and then remove those from that grand number. So the grand number was 1111109, right? Because that's how many values of S we can get. Well, the number can be written as follows. We can have S over 2 times 3 times 5, and that will be S over 30. So the number of values of S will be, in this case, 29. Right? 1 through 29, basically, when you have a fraction like this. This will give you a repeating decimal that has a shorter sequence than 6. And these, of course, came from the prime factors that we originally had up here. Let's see, what other ways can I get shorter sequences? If the fraction is of the form S over, and this is of course m over n, 2 times 3 times 5 times 11. That will also give shorter sequences. Repeating sequences perhaps, but definitely shorter than 6 digits that repeat. And this is S over 330, and the number of values of S here will be from 1 to 329, so that's 329. And there's one more that will give shorter sequences, and that is S over 2 times 3 times 5 times 37, and that is S over 1110, and the number of values of S there obviously will be 1109. And there's no other forms of S that we need to consider. So, what is the total number of values of S? Well, it's not as simple as just adding them. There's an overlap here. And after you study the overlap, you will find that the total of these is actually 1. You get 1109 plus the 329, but you have to minus that 29 to account for an overlap that exists. And that will give you the number of sequences that you have to subtract from the grand total. So to get our F, which is the actual number of fractions m over n, it would be the grand total, which is 111109, minus these guys. So 1109 plus 329 minus 29. And when you do that math, you get 1109700. Now, P is the number of digits that are in F. And as you can see, this has 7 digits. And G is equal to F plus P. So that would be 1109700 plus 7, which is, of course, 1109707. And now, finally, we have to calculate the sum of the squares of G. In particular, the sum of the squares of the digits. So here's G. Sum of the squares of the digits would be 1 squared plus 1 squared plus 9 squared plus 7 squared plus 7 squared, which is, of course, 1 plus 1 plus 81 plus 49 plus 49. And that is equal to 181. And therefore, the answer to this most challenging question and time-consuming question is 181, which is choice E.